Красиво. Мгм. Where is Matt? Where is your device? Matt made a project in machine learning class to say bless you automatically if somebody sneezing. Um, okay, let's begin our second week, and this week will be about deep learning because all large language models are based on neural networks. So today will be not today. This week will be a kind of revision of standard neural network architectures. But so because I'm using these slides first we'll talk about count-based methods for sentence classification. So last week we worked with words. This week we'll work with sentences, like larger structures. Um, so I will skip classical methods because we covered this in machine learning class, like back of words, and we will start with neural networks. Um, so I can just scroll these slides. Well, the first slides are about data sets and different classification tasks. For example, um, it can be binary classification, but it can be multi-class classification, and it can be multi-label classification. Like in this example, when we want to classify by multiple classes our tweet. So there are different data sets. And again, now you can use large language models to generate data sets. And these data sets are used as a benchmarks. They have different number of classes, labels, different topics, sentiment, questions, uh, and different size. So I will just go quickly through these slides until neural networks. This is how NLP looked like before large language models. People try to build so-called semantic trees. I even don't know how they were built. And you can see that so some data sets have labels for the entire tweet, for example, or document. In semantic trees, they had labels for subtrees as well, for some word pairs and so on. So different, yeah, some data sets have also title in addition to the text. And this is a general pipeline that will work also and for neural networks. We have input text, we have some model, and it can be count-based model, it can be neural network model. And this model provides as output one vector, and we apply logistic regression to this vector, and logistic regression uses softmax in the output, so it will provide distribution of classes. So The classical methods, we'll talk about this on machine learning. Also, I will skip generative versus discriminative. It's just general information. The classical methods used naive Bayes for there's we have some students who didn't take ML class, so we will have this homework on naive Bayes in our class. So you will familiarize yourself with count-based methods. Or any other models, because if we have word embeddings, these are features, and we can apply any model like support vector machine or regression. So I will just skip now these slides. Okay. Because otherwise we would need to spend one more week with that. Well, maybe we can just look at this slide. So these count-based methods, they count frequencies of the words, but you can see in this example that the phrases, sorry, with the same words can have different meanings. So this is where count-based methods actually can fail. Because the count of words will be actually exactly the same, but first is good, the second is bad. So we will skip this. Okay, neural network methods. So the pipeline will be exactly the same. We have input text, and in the output of our neural network, we want to have one vector with number of features the same as the number of classes that we want to classify for. If it's binary classification, then 2 classes. It's multiple classes. And do you remember which loss function we apply in the end to get probabilities from this vector for classification? Which loss function we use in Torch?
Is it binary cross entropy?
If it's 2 classes, if it's more classes, just cross entropy. Yes, just cross entropy loss. So cross entropy loss, actually, it's the same as softmax in logistic regression. I can maybe remember the formula. So it's you remember last time we talked about entropy? It was probability times log of probability. Cross entropy they measures distance between 2 distributions. So it's probability of one distribution times log of probability of another distribution. That's why it's called cross entropy. But again, in machine learning class, we will spend entire week to derive this loss function from maximum likelihood principle. Okay, so we have every sentence we can tokenize, and we can use the dictionary of word embeddings like word2vec to represent every token with a vector. And these vectors will be input into our model. neural network. But the output of our model should be just one vector. Because, for example, if you think about recurrent neural networks, they can return the same number of outputs as the number of inputs. If you think about convolution neural networks, they also use this sliding window, and the output will be the same number of features of how many times the sliding window went through our data. In case of text classification, the output should be just one vector. And after that, we again apply softmax and cross-entropy loss, and we get the probability of the entire text. Is it the probability distribution? So how to get one? I don't know. Should I recall what is the neural network? What is so, guys? Who didn't work or doesn't remember what is the linear layer in neural networks? So, okay, I will just remind briefly. So if we have the input vector like this, then this vector may have, let's say, n features. So it will be n times 1, n times 1. But in our classification problem, the output number of classes can be a different number, for example, k. So we want to get in the output the vector of shape k by 1. So how to transform vector of dimension n into vector of dimension k from linear algebra? So let's call this vector x and this vector y. Just multiply by a matrix. So if you multiply x by a matrix of shape m times n, okay, sorry, k times n, and multiply this matrix by vector of size n, you will get as output the vector of size k. And also we can add a so-called bias term, a constant, k times 1. And this is what actually is called linear layer in neural networks. So there k times n plus k times 1 parameters, trainable, learnable parameters that we call weights and biases. Then you can actually stack many linear layers. And typically, we don't use just one linear layer. We use just a sequence of linear layers. So we can apply one linear layer. So to get from input x some intermediate representation, for example, x1. Then we can apply another multiply by another matrix to get another output, x2, and so on. And finally, we will get y. So this is just one operation, but you can then multiply y by matrix, another matrix W. It will be um, a two-layer perceptron or two-layer neural network, and so on. But if we stack linear functions, we will get a linear function. In neural networks, we also add non-linearity, and after the linear output, we also apply non-linearity, which is called activation. So some function, and this function can be any non-linear function, and typically we will use this one, ReLU, rectifying linear unit. So this is kind of like brief introduction of simple multilinear perceptron, simple neural network. And this is how you can get from a vector of arbitrary size, a vector of the size k, where k is the number of classes. Okay, so yes, here is this linear layer. It's just a matrix, maybe plus bias, that transforms one vector into another. And if you think about this matrix W that I erased, so we multiply our vector X by a row of matrix W to get the first component of vector Y. Then we multiply vector X by the second row to get the second component. And you can represent this operation by the rows of our matrix. And then it's exactly the same as logistic regression, just k, in this case, three k linear functions with different parameters. So this is just this representation. There is a transposition missing for this vector of biases because we use transpose vector. Multiplication will be a row. Because these vectors in the rows, they will correspond to each class. If it was noticed that these vectors will actually point into the direction of our sentences, which belongs to this class. Just interesting observation. Okay, so a little bit about our loss function. Our model provides the probabilities, softmax, like the numbers that sum up to 1. So this is the output of our model, y predict. Then we have the true classes, true labels, y train. And the cross entropy will maximize the probability of the class, of the correct class. And as you remember, when we maximize one probability, oops, oh, maybe it will be on the next slide, then the other probabilities will actually go down. I think it will be later. Yeah, and here's the illustration of the process. We have one sentence, we get some, oh, I think, okay, we don't see the illustrations, the moving images, because it's on the course web page. Oh, yeah, so here's the illustration. So then we have the other sentence. Again, we calculate a vector, we calculate probabilities, compare with target, adjust the probability, other probabilities go down. Then we read next sentence. We get the embedding for the sentence. Again, adjust the probability and continue this process. This is how the training process goes on. Okay. So now let's talk about how to get one vector from multiple input vectors. The simplest architecture is just to take the average. We have the rod embeddings, we sum up these embeddings and we get one vector representation. And it's the same idea as we did last time. You can use also learnable weights for these inputs. And then it's called attentive max pooling. So we will talk about attention maybe on Friday. So you take the sum, but with learnable weights. Some words will get high weight, some words will get low weight, and we hope that these weights will choose the words more important for our classification. In count-based methods, these weights were actually fixed, and we used TF-IDF, which is the frequency of the growth in the document times the inverse frequency, that's why IDF, of the documents with this growth. And this D should be the lowercase because word belongs to the current document. It should be the lowercase here. So these weights can be fixed or they can be learnable. And you can think about this as a bag of words. The next architecture is convolutional and recurrent neural networks. I think maybe we will talk about convolution neural networks and we'll go to the code example. And or I can first go through the models and do the code example in next class. What do you think would be better to go like model code, model code, or all the models and then code. Okay, so we'll do just convolutional for today, and next class then we'll go to recurrent neural networks. So I will skip these slides because who took the convolutional neural networks, they know that it will look at the patches of the image and it will help to detect an object in different place. How it works in text. In text, also the keyword can be in different position, and we can, when we apply convolution, we look at the different places in our sentence, and it will help us to detect the cat in the image. So the key phrase in the sentence. But what we are doing next, if we just take a bunch of convolutions, how actually we will get, how actually neural network will understand what was the object on this image. Do you remember? We applied after that max pooling because this combination of convolution and max pooling then actually helps to find the object unrelated to the position on the image. So the same idea will be here. We apply, in this case, free, what's called kernel, with kernel 3 convolution. It means that we look at 3 words at a time. Actually, I maybe should remind you what is the convolution neural network. So when we have 3 word embeddings, how do we get this vector? Just one vector from 3 vectors. Do you remember how the what does it mean, convolution neural network? We multiply these numbers by a matrix with learnable weights. So we introduce a matrix of this shape, in this case 4 by 3. So this will be matrix which is called convolution kernel. So every feature will be multiplied by a weight. And after that, what we're doing after that? I don't remember. How do we get this this first element?
We add the columns together.
We actually add so we multiply every feature, let's call it x1, x2, and so on, x2, and so on. Well, this will be, I just will use another character instead of using multiple indices, y1, y2, and so on, z1, z2, and so on. So we multiply the features with weights. So we multiply let's see, x1 by the first weight and add all these weights multiplied by the features. So we multiply element-wise our matrix W with these vectors and sum up all these numbers. And this is how we get the first element here. And we call this channels. So this dimension we call channels. And when we multiply one matrix W, we get just one channel in the output. If we want to get two channels in the output, we introduce another matrix, another kernel. So this is W, for example, 1. If we want to get the second channel, we will use W2. If we want to get 100 channels, we will use 100 matrices. So this is how convert. But and next, we move to the next 3 tokens and apply the same operations. We multiply by matrix W1, we get the first channel here, multiplied and sum up, multiplied by W2, and then we move to the next 3 tokens, and as the result, we will get a little bit less vectors. In this case, we will get n minus 2 vectors. Because after these last 3 rods, we don't have another rod to apply our convolution kernel. So this is how the convolution works, but we want to get one vector in the end. So how to get one vector? Apply pooling. So after convolution, we apply nonlinearity, and after that, we apply pooling. So pooling means, in this case, it's global pooling. The next slides will show how pooling works, but it's actually taking the maximum value for each channel. And after pooling, we will get one vector and apply a linear layer, we will get the output. So how works this? Okay, this is just illustration. Again, it doesn't work in slides, but it works here. Somewhere. Yes, it works here. So we look at 3 rods at a time, and we provide new vector. And after that, we will apply nonlinearity, max pooling, and we are done. We get just one embedding. So what is this? This is just another representation of convolution. Instead of taking 3 vectors and we can concatenate these 3 vectors. And then instead of applying 3 different matrices, we can apply one matrix, but by 3 times longer. But it's just another mathematical formulation of convolution. Or we apply 3 matrices to 3 vectors, or we apply one large matrix to one longer vector. So I will skip this. Okay. In convolution, there is such parameter as stride also. You can look at every like shift by one, but you also can shift by two vectors. So it's called stride. By default, stride is one, we shift by one, but you can, if you want to decrease the number of output vectors, you can use large stride two. And kernel size typically used in texts between 2 and 5. Because if you take large kernel size, you will need to use large matrices W, and it will increase the number of parameters. Okay, so what is this pooling, how it works? Here is the illustration. We have vectors, and then we take the maximum element of each, in this case, we call this channel for each channel. And this is called global pooling. Because there's max pooling in vision. Max pooling takes the maximum over the patch. Global pooling takes the maximum over the entire data. Okay, I think we can. These are just illustrations, more illustrations about the difference between max pooling and global pooling. Okay, I think let's see if we have some. And okay, this is illustration that you can use different kernel sizes, for example, and you can use one model with kernel size 2, another model with kernel size 3, the third with kernel size 4, and then you will get just one vector outputs after global pooling, and then you can concatenate these vectors. So in this case, you maybe will get better result because you will look at different neighborhoods of your world. Okay. Also, you can apply multiple convolution layers, like one convolution layer, another convolution layer, but it doesn't matter what you're doing in the lower layers of your neural network. In the head, the output of your neural network, you should have always just one vector that we can classify. Multi-label classification, you can read, okay, and then we will recurrent neural network. So yeah, let's move to the example, the code example. But before we go to the code example, I mean to neural networks themselves, we will need to do a lot of work to tokenize texts, to create word embeddings. But next time we will just use this code and it will save our time. Yeah, in this week I combined practice and homework in one file, because we will do some work here, and then you will just use it for the homework. So we will work with a data set with job descriptions, and the goal will be to predict the salary. So it's not classification, but it's the same idea. It's regression task, but we will use the same architectures. And your pipeline, your model will look like this. We will create one embedding or one convolution layer for the title, another convolution layer or recurrent neural network for the job descriptions. Then we have a lot of categorical features, like the city and so on. And then each submodel will provide just one vector. We will concatenate these three vectors and apply linear layer to get the desired output shape. And then apply MSE loss because it's a regression task. So this is the idea of how we will. But in class, I will work only with one block with title or description. Doesn't matter which column we will use. But in homework, you will add these two more blocks to get the required accuracy. Again, this week is nowadays you can use large language model and feed and title and description all in features just in one in one input. But the goal of this week just to make you comfortable with neural networks with Torch, because next week we will start language models, and after the next week we will start large language models. So I want to understand how these blocks are working, because we will use them as a building blocks for more complicated models, which are transformers. Okay, we have 5 minutes. So we can just start, begin this notebook. Okay, so yeah, and for this week, for the homework 2, you might need to run on GPUs. I mean, it will work without GPUs because, for example, bless you. Let's see if I have the training. Yeah, for example, in my training, I got the desired accuracy in 3 epochs. So um, it's it wasn't so long, but with GPU it will be faster. So let's just look at the data. You can upload the data from Google Drive or from the original Kaggle competition. We read the data. Here is our table. So we have title, description, and some other parameters. Job category, salary normalized, city. So the first step is to look at the target. And you know that salaries are not normally distributed. And we have several people with large income and most people with average income. So we will normalize this distribution. And the common way to make large numbers smaller to apply logarithm. So we apply natural log of 1 plus salary. And after this normalization, we get smaller numbers because models typically predict better small numbers than large numbers. So we will get these numbers as a target. So you will predict not the dollars, but log dollars. If you want to get back, you just take the exponent of this number. Then after that, what's next? Then we split our data into text columns, categorical columns, and target column. The first step is to process your text, to tokenize your text. And I don't know if we have time, maybe we should start this next time. And actually, I was thinking I could fill in the notebook, but then I decided that maybe to write this code in class, maybe will be better for you to just go in the same pace, but it will take some time. So the first step will be to normalize our texts. As you remember, um, to represent, so for example, to split the words and commas, because otherwise it will be a separate token. So it's the result want to get the words and commas separated by space. To use lowercase, to drop most common and less common words. And after that, we will apply tokenizer, and finally we'll create a dictionary where every token will be mapped into an integer. After that, we will use word embeddings, and you can use pre-trained, or we will train from scratch. So only after that, we will be able to use these features as inputs into our neural network. So maybe we will do next time only convolution, and maybe recurrent neural network we will do next week, because I think it will take a lot of time. Okay, let's stop here for today.